Good morning. Hope you're doing well out there in the world. I wonder if I have another pack to open. Hope I do. I do! Great timing. Let's do... Actually, let's turn the music off for this. This is serious. I'm gonna let fate decide. That one. Mewtwo. Interesting. I believe. That one. Okay, right on. Venomoth, Shelter, Salazzle, and a Kingler. Cool. I don't think that's anything new. No, it's all... Yeah. Cool. Grab. Hello, Dillo. Welcome. Let's get the tunes back on. They are a little bit loud. Today, we're going to be doing something slightly boring. Well, not slightly boring. Actually, we'll do this one, so you guys can see both. We are going to do a new tutorial because I want to get better at programming. And this tutorial series that I just bought for 20 bucks or so has a lot of the content that I have been trying to find a good resource for. Just let the mic do its thing. There we go. Like, let's see how we're doing there. Yeah, that's pretty good. I might... Yeah, that'll do. Such as like singletons and stuff. So we'll see.
An outline of what we are going to be covering so that you can get geared up and fired up, ready to start. So the three sections of this mini course are going to be the introduction, where we'll talk about the fundamentals of clean code, my rules for clean code, digging into those rules a little bit and trying to understand what they actually mean and try and understand them through a few examples, although not too many examples at this stage, as we're going to be looking in more detail once we get to how to actually apply these as programming patterns and how programming patterns lead to implementing some of these rules. So that would be the subject of the second section, where we're going to study the top programming patterns. We're going to understand how they work, how they implement some of these rules of best programming practices, and really try to understand how we would arrive at these patterns ourselves so that we know when to implement them, when to use them, and most importantly, when not to. And then finally, the final section, just a quick wrap-up, I'll share with you some of my favorite resources for learning about more programming patterns that aren't covered in this course, as well as some bonus content. In particular, there's a lecture in there about the solid principles, so if you're interested or heard of those, then you will see that is in the end of this course. So let's talk about some of the patterns that I'm going to go over in this course. So we're going to look at the Mighty Observer pattern, one that you may have heard of before, incredibly useful, get to use it all the time, and there's lots of language support for it in Unity and C#. The Singleton pattern, again, a mighty pattern that lots of people will have heard about, very controversial. We'll talk about the controversy. There's the finite state machine and state pattern. These two are kind of interlinked, as you can kind of use the state pattern to implement the finite state machine. Very useful in games, things like AI, so we will be talking about that and applying it. There's object pooling, again, incredibly useful in games for performance. We'll talk about when you use it and how you can use it. There's, again, some built-in tools in Unity, so I'll be covering those. There's the strategy, decorator, and composite pattern trinity, which are similar but all quite different and play different roles, and you can use them together to great effect. And I have done in the RPG series to create something like a special abilities system. So these kinds of things are very useful in games again. And then finally we're going to talk about some UI programming patterns, MVC, Model View Controller, Model View Presenter, and Model View View Model, which is a little bit more exotic. And we'll be talking about those and how we can implement them and which one's most appropriate for a Unity Games project. So that's what's coming up. I'm really excited to bring it to you, dive in, and get started.
Love it. I have a little next button somewhere.
So let me start out by making this rather clickbaity statement and say that you shouldn't use design patterns, at least not in the way that you typically think. We don't use design patterns as a library of tools that we hammer into any problem. This is called the golden hammer syndrome. If you happen to know a tool really well, such as a hammer, then everything you look at, even if it is a screw, is going to look like a nail, and you're going to want to use that hammer to solve the problem. So this can happen with design patterns. People will get familiar with one or two, they will love those design patterns, understand them really well, and whenever there is a problem, they might think about applying the design patterns they know. This is the wrong way round. We should be looking at the problems and trying to solve those root cause problems rather than trying to find a solution that fits. It's good to study design patterns as a way of seeing how certain templates of problems have been solved, but often you'll find that once you're really good at programming and design patterns, you find yourself writing design patterns and then only later realizing that you used a design pattern. That's the thing about design patterns. It's often very easy once you understand the reasoning behind them to just simply reinvent them as you need them. However, in this course, we are going to study them as a way to reinforce our understanding of good programming principles. So what are those good programming principles? Well, I've put together my 10 coding commandments, which as a proviso I should say are more like guidelines, because a good programmer will also know when to break the rules. These are things that I've put together and learnt in my experience as a programmer. You may come up with different ones, you may disagree with some of mine, that's great. It happens all the time with programmers. Programmers like to disagree with each other. So do mention in the comments on this video if you disagree, if you have other coding commandments or best practices that you think should be included here. I went for 10. There are obviously loads more, but 10 is a good number when you're talking about commandments. So commandment number 1 is thy code shall read like English or Spanish or Italian or whatever language you happen to write your code in. Typically people all over the world write in English, which is why I've written the rule like this. And importantly, that should be without even having to include any comments. I think that code should be self-documenting where possible. That means that the variable names and the function names and the class names should really explain what this code is doing, which takes me on to point number 2. Thou shalt take time to name things well. Naming things well is really hard, as we will see a little bit in the next lecture, and so you must take time to think very carefully about good names for things. Giving a good name to something is incredibly powerful. It allows you to reason about it in a way that you couldn't when you didn't have a name for it. Imagine trying to talk about a tree without the word tree. If you were just talking about that big woody leafy thing all the time, you just wouldn't be able to have a decent arboreal conversation. So naming things is important and we should take time to do it. It allows us to read the code easily. It allows us to comprehend our code. Takes us on to point number 3. Thy classes shall do one thing. By this, we mean that they are at a consistent level of abstraction. If you have got an audio class, an audio player, then it should only do things relating to playing audio. It should not do anything related to animation. That is obviously outside of the remit of the one thing that class should do. Now, obviously, the levels of abstraction here can change. You could have a class that's responsible for playing the entirety of your game. Obviously, within that remit, it does a lot of things, but it probably farms out some of that work. Similarly, you might have a class that is super narrow-minded that just perhaps spawns an object. And that goes for functions too. Functions should just do one thing. You don't want a function that is print this error message and then do that. You want functions that just do one thing within their level of abstraction. Again, there'll usually be a lower level of abstraction than the classes they reside within, but that's the important part. Number 4, thou shalt use as little state as possible. We'll get into why this is a problem in the next lecture. Often a source of bugs is that you've got mutable state, things that can change, variables that can change, and each variable that can change represents a different state that your program could be in. The more variables you have, it gets exponentially more states that your program can be in, and so these are more states for your program to go wrong in. So using less of that makes your program easier to reason about and less bug prone. We'll talk a lot more about all of these points throughout the course, so this is just an overview at this stage, and we'll go into far more detail, so don't worry if you don't understand everything at this stage. Thou shalt not refactor before the third repetition. This is point number 5, and essentially what it's saying is that we need to be able to see a pattern before we refactor.
1 second. I just need to reply to my massage. Give me a sec. I'm nearly ready. Oops. Gorge. I should send it on my PC. Give me a second. Let me just put on my large camera. Teams. I'm just sending a file to someone. To the lovely Mimi. Pictures. Professional photos. R&D department. To Mimi. This one. Booyah. Booyah, okay.
Factor for that pattern. If you've done something twice, it may not. Is at point number 5. And essentially what it's saying is that we need to be able to see a pattern before we refactor for that pattern. If you've done something twice, it may not be a pattern yet. It might not be something that needs a method taking out or a class creating or any of that stuff until you've done something that for the third time often, then you might find that it is time to create a new function to abstract that shared functionality or a new inheritance hierarchy, those kinds of things, usually you need to see a pattern emerging first, so don't do that too early. Number 6, thou shalt not use static and global state. Again, we'll see this in a couple of lectures' time. It goes hand in hand with point number 4, which is to use as little state as possible. Global and static state is doubly bad because it's more state, but also it can be changed anywhere and accessed anywhere in your program, so it has a lot more possibility to go wrong and to make other things go wrong in your code. Commandment 7, thy classes shall be highly cohesive, goes hand in hand with commandment 8, thy classes shall be loosely coupled. If you have never heard of these two terms before, I'm going to go into detail on these in a couple of lectures' time, so hold your horses and we will understand it better then. Commandment number 9, thou shalt use composition over inheritance. You may have come across the idea of composition. You almost certainly came across the idea of inheritance. Inheritance is where a class is said to be is a something. So, for example, you might have a crocodile is an animal. Those are the kind of is a relationships. Composition is typically a has a relationship. A car has a wheel. So you might have a car class which has a wheel class. And typically we prefer to use composition in programming because it allows us for a lot more flexibility. Again, we'll cover this a lot more in a couple of lectures' time. And finally, 10th commandment, thou shalt follow the law of Demeter. I find this the kind of the least important of the commandments, but it is a useful guideline. And as we'll see later, I will indeed be calling it the guideline of Demeter because I think it is a rule that you will be breaking reasonably often, which is why I put it as the last commandment. Okay, so these are my 10 coding commandments. I'd be interested to know what your best practices are. Please go and share them in the comments, and we're going to be using these best programming principles to understand and evaluate the design patterns that we will see later in the course. But in the next couple of lectures, we're going to dive into a few of these to try and unpack why they are important.
Cool. I don't care about community and support.
So here is a very commonly repeated quote about computer science. There are only two hard things in computer science: cache invalidation and naming things. This is usually attributed to Phil Carlton, an engineer who worked at Silicon Graphics and Netscape, among other famous companies. And this is a very, sometimes added to this quote, by the way, is and off by one errors. So there's only two hard things: cache invalidation, naming things, and off by one errors. I tend to think that really the first two are the most important, although that second one is kind of funny. So what is cache invalidation? We'll get to naming things in just a second. I think it's the easiest thing to unpack. But cache invalidation doesn't necessarily mean something if you haven't necessarily got a theoretical grounding in computer science. So what do we mean by caching? Well, caching is when we store a value that, for performance reasons or for ease, we could have just calculated. So, for example, we've got a square, and the only information we need to know about or rectangle in this case, only thing we need to know about a rectangle is its width and height. And from that, we can have set width, set height on this, if this was a class. We could also have a get area method, and we could calculate the area using the width and height by multiplying them. However, if we decided, we want to do this for performance reasons, or just for simplicity's sake, we didn't feel like writing a getter, we'd just go and store the area in a new variable. So we've just added another piece of state, another variable into the mix in this class. And because it's a cache, because it is derived from other data and could easily be rederived, there's a problem of invalidating this cache. Every time I call set width or set height, I need to remember to write code that updates the area. Otherwise, this cache becomes invalid. The variable stored in the area is now no longer the real area, not representing the current width and height of this rectangle. So that all seems like, okay, well, I've just got to remember to store it in two variables. I can go ahead and do that. And at the time, that will seem like a good idea. Then somebody else will come along and write a method like double width and height. And you and they won't remember or won't know that area is a cache and needs to be updated every time width and height is updated. So they just go ahead and naively double the width and height and think everything will be fine. It isn't. Area becomes invalid every time this method is called, and that is how bugs are introduced via cache invalidation. Now, this is a trivial example. However, in reality, these bugs get far more obscure and hard to pick up. So that's why it's really important whenever introducing new variables that you think very carefully about, am I caching something? Could I just calculate this some other how? Here are a couple of common signs that you can look out for just to save yourself the hassle of introducing the caching in the first place. If in doubt, calculate, don't cache, and even if it's not that efficient, you think it might cost you something in terms of efficiency in the long run, trust me, it probably won't, and it will cost you in terms of bugs. So a common thing to see is Boolean flags. If you've got a Boolean around the place, for some reason, Booleans tend not to be state. There are some states, but for example, a common Boolean flag might be is jumping. Could you not calculate whether you are off the ground instead? Is there some other way that you could calculate whether you are jumping rather than storing a Boolean variable about that? It's probably derived state. You can probably, in a lot of cases with Boolean flags, you can calculate that from some other state. So that's an important one. Get components. So this is Unity specific. When you have get components and store the result of that in awake, you're actually caching the result of that. What happens if a new component is added later on? What happens if that component gets deleted and a new one gets created? Your cache, your pointer to that get component will go out of date. Now, this is reasonably safe in Unity and probably one that you can ignore, but just be aware that that is a cache that you're creating there. It is not necessarily... If you think of the state as being what is the current component on this game object, you're not necessarily going to get that. You're going to get the component that was on the game object at awake. So that was a cache. Having to remember to update something in code. So if you've got some function and you always find yourself saying to yourself, I need to remember that needs to be updated, then you probably have a cache. Updating variables on callbacks is quite a common one. If like on collision and on collision enter, on collision exit, you find yourself, you're again updating something like a Boolean flag or maybe something else, you might find that you have got yourself into a situation where you're having to do that with callbacks because you are trying to keep a cache up to date. It's not to say that all caches are bad and that you shouldn't ever cache, but avoid it if you can help it. Now on to the slightly easier good naming part of that quote. Here are some good naming tips. So typically the measure of code quality is WTFs per minute, or at least that's a nice way to think about it. You want to have whoever is looking at your code be confused as few times as possible when they're reading it. And that includes you in the future. So you want to name things so that everybody understands what you're talking about. That's where good naming comes in. It's all about good communication. Ultimately, code is communication. Something like this is terrible. You've got an integer named t, and then in a comment you're saying seconds since the event happened. So seconds since, I don't know, something like the character was shot or the character died. Those kinds of things. But you've called the variable t. So anywhere where you're using this in the code, you'd have to go and find this place where it's declared, find the comment. You're going to go, WTF, what is this t about? What am I supposed to do with it? If you'd named it something sensible to begin with, like seconds since event happened, even if it's a long variable name, everywhere that variable is used, you will know exactly what it's for, and it's going to be clear to the reader of the code, including yourself in the future, that this was what it was meant to do. General rule of good practice is that classes should be named as nouns. Avoid names such as manager, controller, processor. It's really not clear what a manager does or what a controller or processor do. They are kind of cop-out names, in my opinion. We add them because we don't really know what this thing is supposed to do. It's an audio manager. What does it do in audio? What exactly is its purpose? Is it an audio source? Is it an audio player?
yeah, I use oops, no. I use manager and controller all the time. Hello? Why is that not playing?
Is it an audio source? Is it an audio player? Things like that are much more meaningful than calling it a manager, a controller, or processor. So if you find yourself, and I find this quite often, that I want to call something a manager, stop and ask yourself, what does it actually do? What do I really want to call this thing? Methods should be verbs typically, so you do something with a method to a class, which is a noun. So those are good rules to follow in terms of object-oriented programming. And be consistent. Once you've chosen to call something, use that term all the time. Don't go switching between terms and confusing the heck out of somebody who is reading it. Something like fetch value and then later having a get value and a retrieve value will leave people wondering, is fetch different to get, or is retrieve different to fetch? You just don't know as the reader of that code. If you have chosen the exact same word, then you are sure that the same thing is probably happening. And finally, if you're not sure, go and talk to somebody else about how to name something. You'll often find that they go, oh, well, what you're talking about is blah, blah, blah. And they know exactly what word you intended to use, or so on.
Right.
I will often find that I have very lengthy discussions about naming something well. We do this inside the team very regularly. We'll go and talk about, like, what should we call this? And we'll spend 15, 20 minutes talking about naming something very specific. And that's because naming's so important in communication. So don't underrate it. Spend time on it. Good naming will save you a lot of time later on. So there are going to be lots of challenges like this one in this course to share your own examples from your own experience, because I think this is much more interesting than my clinical examples that I can come up with on the spot. So where have you used cache in your code? Go and share in the discussions for this lecture. Where have you cached something? Where have you ever had a cache invalidation bug? Not everyone will have had this if you've been programming for a short while, but if you've been programming for a long while, I'm sure you have. Can you point to any cases where you're like, darn it, I should have updated that variable and I forgot to, and it led to a bug? What is your variable name of shame? What is the worst
quite often
name
use
given
timer.
to a variable,
Just timer,
function,
not
or
very good.
class? And let me know down in the discussions. I would love to read and share my own there as well. In the next lecture, we're going to be looking at the sources of spaghettifying in your code. And I'm not talking about the kind of tasty sources, I'm talking about the points where So let's discuss a few of the sources of spaghetti code. But before we do...
I'm going to go make a coffee before this. And maybe put my standing desk up. I can feel myself fading. It's a little bit too low still. Sounds like something's getting pulled. Ah, that'll do. Alrighty. Large camera on. We're back. I have a coffee. Spotify's not playing. I thought I set that to play. This is my favorite mug. It's very cute. I bought it at a medieval fair from a lovely lady for like $15. Maybe more, I forget how much.
Do that.
Alrighty.
Let's ask ourselves, why is it called spaghetti code in the first place? It might not be obvious to all of you. So if you've heard this term before, what it's getting at is the idea that when you've got a bowl of spaghetti like this and you pull at one strand, you're not sure which bits of the bowl are going to move. Where is the end of that spaghetti? Where is it? It's in a tangle. You can't quite see. Spaghetti code is like this. You change one bit of code and you are not sure what the repercussions are going to be. It could be wide-reaching and have a bug in a piece of completely unrelated code, or at least you thought it was unrelated. So that's why spaghetti code is bad, because you go and make a change in one place and it has repercussions all over the place. What we want is you make a change in one class and it's mostly self-contained to that class with a little bit of changes elsewhere. Now, the static and global state are some commonly, identified issues with code. Any use of static and global state is a bad thing. So, what do we mean by static or global state? Well, it's these cases where you have a static public variable, even not necessarily public, but a static variable that's shared across the whole of your program. And you can edit it. If it's constant, that doesn't just
that's not
plug
static.
that way. But if it's something that can be modified by your program, then there is an issue. Here's why. Bugs, that's the first thing. It's quite easy for that variable to change when you're not expecting it to, because somewhere else in the code it gets updated, you forgot that, because your mind can't be everywhere in a large code base, and so bugs happen. Poor unit testability. So this is not always a problem in games because we don't always unit test games for whatever reason. That might be a bad thing, but we don't often unit test games. But if you've got global state, it makes it virtually impossible or very hard to unit test things properly, because you can't set things up in isolation in a little test case. Code comprehension. Because global state variables are often declared far away or used far away from where you're currently reading the code, and their impact can be far away, it can be really hard to understand. When is that variable going to change? What should that variable be at this point in time? So someone coming into your code fresh, or you coming in a few months' time, you won't be able to know what to expect from that variable. Multi-threading, not so much an issue again with Unity, because we tend to write single-threaded code, but if you do have multi-threaded stuff, then this whole level of bugs just gets so much worse, because threads can stomp all over each other. There can be performance issues around having multiple threads trying to access the same information and communication between threads. Its global state is absolutely a no-go when you've got multi-threading involved. And the last final argument is, and then you need two. So you thought with that global state there'd only ever be one audio manager. You thought there'd only ever be one character in the game. Oh, suddenly we've decided we're going to have a team of player characters in the game. And now you thought that it was all right to have just one global mana variable. Well, now we need two mana variables, one for the player 1 and one for player 2. Wouldn't it have been better if we hadn't used global variables in the first place? So these are some of the common reasons we don't use global state. It creates spaghetti code where we don't know what is involved with what. Here's an example. Suppose we had a mana variable, like I was saying, and we decided it would be a good idea if this was a publicly static global variable. So in our character, we might decide that we're updating the mana every frame to recharge, and when you use an ability, that cost gets subtracted from the mana. Obviously, we'd put in some code here to make sure the mana doesn't go below 0 and stuff like that, but for simplicity's sake, we're just leaving it like this. Now, suppose you have another class somewhere else, a magic potion, that will restore your mana. Now, for simplicity, because it can just get access to the mana, it just does. It goes and restores that mana. Everything's working fine at the moment. What if I went in and added some code that tried to cap the mana?
Yeah.
Well, I would go and write it here where the mana's being updated, right?
Yeah, you'd think so.
Yes, except I'd introduce a bug because I could overcharge the mana by using a mana potion because I'm accessing this global state and I didn't realize it. It was coming out of left field for me. I didn't know it was there. Another source of spaghettification is communication between classes.
Yes.
And this is where those 2 points of high cohesion and loose coupling come into the equation.
Yep.
So what is loose coupling and high cohesion? Well, I think this diagram kind of sums it up the best. Imagine that these boxes are classes, and inside them the dots are variables and functions.
Yep.
And the lines between them are when a function accesses a variable or another function, and so on. So what's going on here is the good example at the top is one which has high cohesion and loose coupling. What do we mean by that? High cohesion means that the elements within the classes, the functions and variables, refer a lot to one another. The functions use multiple variables, they use each other, and so on. Loose coupling means the opposite is true between classes. One class will not try to access lots and lots of variables of another class. That's what happens when you have the bad example down here at the bottom, which is one that has low cohesion, meaning that the elements within the class don't really refer to each other very much, and tight coupling, which is when they actually refer a lot more to elements from other classes. You can see these two classes have a lot of functions and variables that reference each other.
One sec. I need my bonk sticks. I need this window open as well. Yeah.
Across the class boundary, which means that these two classes are very tightly coupled. And this is usually a sign that your structure of classes isn't very good, and you should consider rejigging the classes and their responsibilities so that they can be have higher cohesion and more loose coupling. So here comes an example of this and a challenge for you.
Ooh,
Why
challenge.
are these two classes here bad?
Okay, so we have on the left we have a character class that's got a bunch of serialized fields. It's got an animator, an audio source, and an audio clip. It's got a health. We've got a knockback, just setting the trigger knockback in the animator. We've got a shout in the audio source, and we've got a take damage. We've got an enemy, which is referencing the character class. We're finding the object of type in start, and we're attacking, and we're calling all those things in the character. Well, why don't we just put the attack method in the character and then call that method? That's what I would do.
Pause the video and have a go and see if you could also rewrite it to be better.
I'm not going to rewrite it, but I would move the attack over and just call it from within the function, or within the class.
Okay, so this, if you hadn't figured it out, it was low cohesion and tight coupling was what was wrong with these classes. So here's our low cohesion character class, which you can see what's low cohesion about it. Well, this knockback method only uses one variable, the animator. The shout method only uses the audio source and the shout, and take damage only uses the health. So you can see that essentially we've almost got three separate classes here. We've got one that deals with the animation portion, which is this knockback method, one class that deals with the audio portion, and one class that deals with the health portion. So it's not very cohesive. We could split it up and there wouldn't be much communication between those classes.
True.
And we'd end up with more high cohesion. Now, how about the tightly coupled enemy was the other problem, because this enemy knew an awful lot of information about the character. For instance, it knew all of these methods. It used 3 of its methods here when it only has 3, so that's pretty tightly coupled. And then we also knew how to access and how to find this character. So in start, it's actually finding the character. That's another thing that it needs to know about that class. And if we change where the character is located, if we changed any of these methods, they're all reasons why we would have to come and also change the enemy. So spaghetti code is when you make one change in one file and you have to change 15 other files. Good code, you should make a change in one file, maybe 2, but that should be it. If it's good code, it's resilient to changing and doesn't need scattershot surgery across the whole code base. So how could we improve this? In a high cohesion character, we might say, well, let's take more responsibility for taking a hit, and that's going to be all rolled up into one method, which accesses the animator, the audio, and the health components of this character. This is now a high cohesion class because the function accesses multiple of those variables, and it's much more tightly integrated. The loosely coupled enemy, on the other hand, might just, and this is why they go hand in hand, high cohesion and loose coupling, because now that we have a high cohesion character, the coupling to the enemy has improved because we now just call take hit. What I've also improved here is we've used an interface. If you've not seen interfaces before, they're just a way of saying, I want this, it's a contract basically, I want this method to be implemented on whatever object is passed in. So now what we've got is that instead of relying directly on the high cohesion character class, we could even swap that out. Instead of having a character, we could have an NPC object. As long as it implemented attackable, we would be able to call take hit on it. So now we don't even have we're not even coupled to the way of finding that class in enemy.
That's cool.
We just get past that target, and that's how we do the damage to it. Now obviously this is quite a toy example, but you can see from this example how cohesion and coupling go hand in hand. Now in the next lecture we are going to look at composition and inheritance and why you should prefer the former over the latter.
Oh, I'm excited for this lecture series. I've already learnt some cool stuff. Let's keep going.
So the next point I want to dig into is point 9. Thou shalt use composition over inheritance. What does composition and inheritance mean? Why should we prefer one over the other? Composition over inheritance. So a classic example of where inheritance can go wrong is the following. Imagine we start off with an animal class, and that's going to be our superclass. It's going to be what we inherit from. If you are not too familiar with inheritance, this is where we take all of the functionality of this class. Essentially, we say anything that inherits from it is one of these. It has all of that and more. So a mammal, for example, might be a type of animal. Not all animals are mammals, but all mammals are animals. And so a mammal will have all of the functionality of the animal. It will be an animal. So if an animal has a live method implemented here, then an animal also has that live method. It automatically inherits that from the animal class. The mammal, however, can add its own functionality as well. As you can see here, the mammal adds on the functionality of being able to make milk, and anything that inherits from the mammal will be able to make milk. Cool. We might have another subclass of animal which further specializes it or specializes it differently to the mammal, such as reptile, which allows it to lay eggs. That gives it that functionality there. And then we can actually inherit some actual instances or some actual classes from this that we might instantiate, such as the cow or a snake from reptile, and you can see how they're going to get all of the appropriate functionality here. Cow gets to make milk and live, the snake gets to lay eggs and live, and they share the common functionality of living, but they get to differentiate functionality as well. This all seems fine and glorious and really easy
it
up until
does.
the point where you find something that doesn't match your inheritance taxonomy. So you
Yes.
might find something like a platypus,
Yes,
which suddenly
it's
doesn't
both.
inherit from mammal very easily because it wants to be able to lay eggs, but it doesn't inherit from reptile because it's warm-blooded and it needs to make milk. So where do we inherit from? And this is a very common issue with inheritance. You'll find that stuff kind of starts to happen. You'll find things that you want to inherit from multiple places, and languages like C# will not let you inherit from multiple places, because then you wouldn't know, for example, if I were to call the live method on platypus, do I call it via the mammal side or the reptile side? What if the reptile had overridden it? And so it gets very confusing. And obviously a platypus isn't really a reptile, but it does have the ability to lay eggs, so this gets very confusing. Composition, on the other hand, it can be a lot more powerful. It can be a lot more verbose as well. It can mean that we have to write methods that expose the functionality of these components. It can be a little bit more complicated than inheritance, but it can save us a lot of that kind of hassle. So you may be familiar with composition in the sense of Unity components. We can take a game object and add all sorts of different components to it to make it behave how we want it to. So instead of having a player class, we would have a player game object, and we would give it a movement component, we would give it some particle effect components, we'd give it some animator components, and that, the combination of those components, the composition of those components, gives it its actual functionality, and those components have to coordinate between themselves. So we could do the same thing with a cow, and in this case you could still have a coordinating class. You could still have a cow class that coordinates and composes a bunch of functionality driven components. So for example, we might have a milk making component. The cow will have a, so you notice the change in language here. In inheritance we talk about is a, we would say the cow is a mammal. Here we're saying that the cow has a milk making component, and it would need to write some wrapper functionality to make sure it is calling to that make milk function in the right places and so on and so forth, but it is able to reuse that functionality at will. And the snake could have an egg laying component and similarly could call to that functionality, and now the platypus has got a very easy choice of simply including both, being able to have a milk making component and have an egg laying component. And composition and inheritance isn't an either or situation. You could easily have both of these. You could have that the mammal has a milk making component, that you have the reptile has an egg laying component, and then the platypus is a mammal but also has an egg laying component. So you can start to mix and match these things as well, but what we're saying here is that try and put more of your heavy functionality into components. They are far more reusable, they are far more flexible than trying to stuff all of that functionality into parent classes and an inheritance. Try and use the inheritance as little as possible, try and use components as much as possible. And
I love
that's what composition over inheritance means. It is not a hard and fast rule saying that you must use composition all the time and never use inheritance. It's saying try to use one more than the other. So let's have a little challenge to see if you can figure out where this picture goes wrong. This is an inheritance hierarchy, and what I've listed out is some of the functionality that you might expect to see in these classes. So at the top level we've got a character. This is the shared functionality between a player and an enemy. It is able to do locomotion, so moving around the world. It's able to attack. It has health. These kinds of things we want both the player and enemy to have. Great. So we inherit in player and enemy from the character class. The player adds a layer of player control logic. It also adds some upgradability, such as maybe in an RPG you're able to level up your character. The enemy, on the other hand, does not have this upgradability. Enemies are kind of more fixed and programmed into the level. However, they do have AI control, and they are programmed to be hostile to the player when you approach them. This seems fine and great, but can you imagine what you might add to this game that would break or encourage you to have bad inheritance here or mean duplicated code? Have a pause, have a think, see if you can...
My first thought goes to like... maybe a sort of character that doesn't have one of those components, so like an NPC that doesn't move or doesn't have health or doesn't attack. You could also some sort of I don't know. like enemies that you can control. So like, I'm trying to think of like the platypus equivalent of like something that needs AI, like hostile to the player, that is also upgradable. So like, I don't know, some weird edge case that needs both of them. Hmm. Yeah, I don't know.
Think of anything, any type of class here that we'd add and wouldn't match in here. Okay, so what I'm thinking is we could be adding in an NPC. For example. An NPC would need some shared functionality from the character. It would need the locomotion. It would need to be able to, probably wouldn't need to be able to attack. So it's going to inherit functionality it doesn't need. So that's something that's not great already. It's going to inherit a health. Maybe you don't want to be able to kill the NPCs. So maybe it shouldn't be inheriting health either. So you can see how inheritance is already getting us in a muddle without the fact that actually now we're going to have some duplicated code, because we might want to have AI control and share some of that AI control that the enemy's already got, but without the hostility to the player. So we don't want to inherit NPC from enemy, because then it's going to be hostile to the player, and somehow we've got to switch that off, and that's going to be a bit hacky. It doesn't really make sense that an NPC is an enemy. That doesn't make sense from an inheritance standpoint. And one more thing that we can see here is that these classes are violating the principle that a class should do one thing. You can see they are managing many different domains. They are managing locomotion, they are managing combat, health, AI control, all that sort of thing. If we split this into components, it would help on multiple levels. It would allow us to compose something like an NPC very easily. We could include locomotion components, but we could exclude health and attacking. We could include AI control components, but exclude the hostile to the player components, and that makes a lot more sense. Now, what you can do to get a bit of the best of both worlds, and particularly in Unity, is to use the prefabbing system as a kind of layer of inheritance, which would allow you to, say, have a character prefab and then inherit from that, and maybe your NPC wouldn't even inherit from character because all you're doing is adding that locomotion component, but it allows you to group together some of those common groupings of components and have still a kind of inheritance structure for when that is useful.
That was very
so
satisfying.
Hopefully you now understand a little bit better why composition is a good idea, why inheritance sometimes leads us into trouble. In the next lecture, we're going to be looking into the rather obscurely named Law of Demeter.
Cool. What is the Law of Demeter? I have no idea.
So what is this Law of Demeter, or as I'm choosing to call it, the guideline of Demeter, because I don't think it's something that we want to adhere to necessarily too strictly. It needs a little bit of caution when applying it. Now, typically it's referred to as the dots rule, or the multiple dots rule, or the two dots rule. And the idea is that if you see a line this, you're almost certainly in violation of the law.
I hate that.
And let's have a look at this. Why is this a bad thing?
Because
we've got
dots.
A class, we're in some class that has an enemy variable. Maybe that was something passed in as an argument to a function. So we have a dependency on enemy in this class. That's fine. We know about the interface of enemies, so doing a get current target on enemy should be fine. That's a publicly exposed variable. We are depending upon its public interface. That is okay. However, what's not okay is that then this target is of some other type. Maybe it's a player, for example. Maybe it's a character. And we are now calling a function on that. So now we're depending upon that class as well. And then, what's more, we've done another bad thing. Or this would have been bad enough. We're going one step further, and we're saying, well, apart from depending upon the enemy's target class and the health component, now we're depending on the health component as well to do damage to it. Basically, this line is bad because it means that we're depending on every link of this chain. If anything in this chain changes, then we've got ourselves a problem. Now, this wouldn't be so much of a problem if everything in this chain was the same. Sometimes in some languages like Ruby, you'll do this a lot with strings. You'll have chains of string commands or chain of array commands, and each member of the chain just returns another array or another string. So you're not actually increasing the number of classes you're depending upon. But this isn't the case here. Here we are depending on more and more classes, and that's basically the reason that we have the Law of Demeter, because we don't want to, or the Law of Demeter, as some people pronounce it differently. That's how I pronounce it, and it might be wrong. Anyway, the reason we don't want to do this is we don't want to add more class dependencies, and this is an easy way of accidentally adding more class dependencies and not realizing it. It's not the best thing, and often what we want to do is make the class we're talking to have the responsibility for doing more of this. So exposing something higher level from the enemy might be a solution, such as doing damage to the current target.
Yeah.
So that means that the enemy will have to have more code written into it. Maybe the current target and the health component also will need to have more code written into them to avoid these multiple steps. But that does now mean that if we made some sort of wholesale change to the way that the target works, you're not going to have to go and change a whole bunch of other files that are doing lookups, crazy lookups like this. So here's a challenge for you to see if you can identify what is wrong with the code on this slide. So what's the situation here? We've got ourselves a player set up. A player's got a gun. The gun has got ammo, and the ammo class has got a number of rounds. And for simplicity's sake, I've made these variables public, although you could imagine that they were private with getters and so on and so forth. But for simplicity's sake, everything's public in this hierarchy. Then over on the left, we've got some UI to represent the player and represent the gun and the ammo. And this works fairly straightforwardly. We've got a player UI which has some gun UI in it, and when we redraw the player UI, we get some information about the player. You can see we're getting reference to the player. We are printing its health. In lieu of actually updating some UI, we are printing the health, and then we are calling redraw on the gun UI, and the gun UI similarly gets some information from the player and prints the rounds left. What looks wrong in this slide? Pause the video and see if you can figure it out. If you
To me, there's a few things. I don't know why we need an ammo class. We could just store rounds left in the gun. That's problem number one for me. So that we wouldn't have to do player.gun.ammo.rounds left. We just have to do player.gun.rounds left. So we're cutting out ammo. And then I also dislike how we're finding the player twice. I'm not a big fan of that. And then also, why do we need gun UI? Can't we just redraw that all in player UI? That would be... Yeah, so I'd move this up here. I'd get rid of ammo. I'd move this into the gun class. Get rid of the ammo class.
and figure out what's wrong. Bonus is to try and fix it. Okay, welcome back. So if you've had a go at this, then you will be saying, well, this line here looks a bit fishy. That seems to violate the law of Demeter, because our gun UI has to have a dependency on player, has to have a dependency on gun, has to have a dependency on ammo, and it has to have a dependency on rounds left. Doesn't seem ideal.
Gross.
So what could we do to improve this situation? Well, it's not always as straightforward as saying, well, let's just have the player have a get rounds left method. Maybe that's the wrong level of abstraction for the player. I think here the first place we're going wrong is by having the gun UI get hold of the player for itself. The gun UI doesn't really have to be linked to a player at all. It could just be passed a gun or given a gun from somewhere else. So let's see if we can't do a better job of this. So the first thing I said was over the gun UI.
We're getting the gun from the player.
We want to
just
not
be given
worry
a gun
about getting hold of the player here in the gun UI. In fact, I don't even think we should know about the player at all. It's a gun UI. It's not a player gun UI. So let's try and reduce the number of dependencies here by passing in the actual gun
Yeah.
type here that we want to redraw, that we want to render. So now what we can do is we've simplified matters a little bit. We've got none of this dealing with the player or figuring out
Yeah.
how to get hold of the
Just give him
player.
the gun.
And instead we are just getting hold of the gun, .ammo, .rounds left. This is still not great, but we'll come back to that in a second. The player UI now would be the one responsible for when it calls gun UI and does a gun UI.redraw UI, it would pass in the player.gun. And that's
Yeah.
fine because it has a dependency on player.
Yeah.
It has an unfortunate dependency that I don't quite like, but we can probably not get around at this level, which is that it knows how to find player as well.
Yeah, I
That's
also
not
dislike
ideal,
that.
but
Not
it's
ideal.
probably okay. And it can use, obviously, the public interface for player. It can get its health, it can get its gun, and redraw the gun using the gun UI, which it's aware of. So this is no longer so bad. It's not violating the law as badly, but there is still a gun.ammo.rounds left. So
Yeah.
we've got an issue here that
Time
the
to
gun
delete the
UI
ammo class.
knows a little bit about the internals of the gun and how it's storing the rounds left of ammo. And if we were to change how that works, it's going to affect the gun UI. So this is where we do the kind of simpler change of just adding another getter in here in the gun, where we might do something
Okay.
like public, which returns an int, which would be something like get rounds left on here. And we could just go ahead and from here return the ammo dot rounds
Yeah.
left. And now you can see the gun had already a dependency on ammo, so it's fine for it to be getting the rounds left from ammo. It's using its public interface of its direct dependencies, not dependencies of dependencies. And that's the point of the law of Demeter. So now we can fix that up over in the gun UI. So instead of the gun UI knowing about the ammo class, it just does a gun.get rounds left, and that means that the gun UI only has a dependency on gun.
Okay.
The player UI only has a dependency on player and not any of its descendant dependencies. And the gun only has a
Okay, I was
dependency
wrong.
on its ammo and so on. So we've really reduced those dependencies down to the direct dependencies that are absolutely necessary by using the law of Demeter. So hopefully now you'll be more confident in understanding if you ever come across the law of Demeter or Demeter and don't know what it meant in the past. Now you've got an idea and can see how it can help you to write better, more maintainable code with fewer dependencies. So this brings us to the close of our introductory section. Let's review our coding commandments before we dive in to design patterns. Number 1, thy code shall read like English. Number 2, thou shalt take time to name things well. We've seen how important and hard that is.
Yep.
Thy classes shall do one thing, also known as the single responsibility principle, and this is about consistent levels of abstraction. Thou shalt use as little state as possible. State causes bugs.
Yeah, I
Let's
still don't
not
really know
include
what
as much of it as we
they mean by
can.
state.
Thou
but I'm
shalt
sure
not
then.
refactor before the third repetition. Premature refactoring leads to complication, not simplification. Thou shalt not use static and global state. State is bad, static and global state doubly so. Thy classes shall be highly cohesive, and thy classes shall be loosely coupled, meaning that they communicate a lot within themselves and less outside of themselves. Thou shalt use composition over inheritance because it's more flexible and generally more reusable. And thou shalt follow the law of Demeter to not include dependencies that we don't need. I look forward to seeing
Love
you
it.
in the next section where we'll get cracking with design patterns.
Love it.
So let's talk about one of the most commonly used design patterns, or the most commonly talked about, which is the observer pattern. And we're going to start with a motivating example from the game world. So imagine that in my game, I have a rampage mode. I get some sort of power up and I become invincible and scary to enemies. So usually enemies will try to attack me. However, if I get a rampage power up, I become invincible. And as a result, enemies should try to run away now. But a few few other things happen in the game as well. Apart from that, that's not the only behavior that people see. They will also see that their health component should stop registering damage, and that the UI should be tinted red or some other kind of UI update and indicator. So the situation we've got is a lot of dependencies. We've got a rampage mode component of some sort, which gets enabled when we pick up that power up. It kind of detects the power up somehow. Let's just assume that that bit is sorted out. We've got the rampage mode has to talk to a whole bunch of enemies. It has to call a method on the enemies to say, hey, you should be scared of me right now. So in a naive example, this might do a find object of type, find all the enemy AIs and call a method on them saying run away, something like that. Now, this has obviously created a dependency between Rampage and the enemy AI. It's made Rampage dependent and coupled to the enemy AI. It also, if we carry on with this naive train of thought, if we have a Rampage UI, it has to go and say, hey, get the UI and update it. Tell the UI that we're in Rampage mode and draw the red tint. And go to the health component and say, hey, enable invulnerability. So it's got all of these dependencies all of a sudden. It knows a lot about all of these different classes, which is not an ideal situation to be in.
No, it
what
is
we
not.
want to do is essentially flip this around, because this would take it from having one class with a dependency on lots of classes to a lot of classes having a dependency on one class, which is a much better place to be in this case. And one naive way of doing this is in update. So the Rampage UI could, every update, check with the player's Rampage component and say, are you rampaging? And if so, I should draw the Rampage UI. The same could go with the health component. It could check against Rampage and it could enable its invulnerability, and all of the enemies could run their update methods to check that as well. Now, this has an efficiency problem because update will be run every frame, and Rampage might be an event that happens once or twice in the whole course of the game. So this is an okay strategy, but not ideal, and it's also not great from the point of view of understanding the code. So what could we do instead? So that's where the observer pattern comes in. Now I'm going to use this graphic, which is a UML diagram taken from Wikipedia, because I think it's time that we start to understand these kinds of diagrams. We'll see them all over the place wherever design or programming patterns are discussed. So we're going to try and understand what this means. So the key things in the observer pattern are the observer class, which is this thing over here, and the subject, which is something over here. The subject is the thing that we are observing. The observer is the thing doing the observing. In our example, the subject here would be the Rampage component. The observers would be a number of different classes. They would be the enemy class, the Rampage UI class, and the health class. So what's going on here? Basically, the observer has an update method, which basically is saying something has changed. For example, Rampage has started, Rampage has stopped. That would be our update method on the observer. And then you can see what we've got here, this arrow, this empty white arrow, is indicating inheritance. So we've got a concrete observer A, a concrete observer B. In our example, this would be an enemy, this would be a health component, and the Rampage UI. Each of these implements the update method, so each of them would have Rampage enabled, Rampage disabled on them, and you can then have a situation where they register themselves for notifications. So you can see the subject here has a register observer, unregister observer, and notify observers. So what would happen is the health component would call register observer on the Rampage component. The enemies would do the same. And then when the Rampage actually starts, the subject, in which case the Rampage component, would notify all of the observers. It essentially runs through, as you can see this little snippet of code here, notify observers would go and do a for loop over all of the registered observers and call their update method. So this is obviously not exclusive to rampaging, and it is a very common pattern to want to use when in a situation where you have a one-to-many kind of communication, where you have one class, the subject, that wants to send a message to lots of different observers and doesn't particularly care who those observers are. We don't want to have to know who needs to update as a response to this. It's just a fire and forget kind of situation. Now, there's a lot of ways for us to do this. This is the kind of classic way, is to implement all these methods, but there's a lot of better ways for us to do this in Unity and C#. So we're going to look at some of those methods in the next lecture. But for now, let's have a quick little challenge about this pattern and have a think about the principles that this pattern is trying to improve. So take a look back at the commandments from the last section, and which does this particular pattern implement? Pause the video and have a little ponder.
So we're at 537. I think it's mostly like decoupling and yeah. Let's do it. Why not? It was in here somewhere.
Tracking.
Yep. It doesn't affect number 1. It doesn't affect number 2. It is in accordance with 3. I don't know about 4. It doesn't affect 5. Doesn't affect 6. I think it's 7 and 8. It's kind of going against 9. It's using inheritance, and it doesn't affect. It does affect 10, so it's kind of 7, 8, and 10. It's making. I think it's mostly about 8. In the coupling is much less.
Ponder. Okay, welcome back. So what I think this implements is not super clear necessarily straight off the bat, but this is about loose coupling primarily. We had a situation in the first naive implementation of Rampage where Rampage was unnecessarily coupled to a whole lot of components, which is undesirable because any of those components changing would cause a change in Rampage. So what you're doing is you're reducing the coupling essentially by changing the direction of those dependencies, and that's why we like to use things like the observer pattern. Okay, so that's the observer pattern in a nutshell. In the next lecture, we're going to look at how we can actually implement it using various Unity methods.
Hell yeah. I think we'll do just this one and then go. I imagine I'll need a Unity project. So let's get that happening. And we'll make a new repo just for fun. Logo creation, cut out Matt, I'll push that, why not? Let's make a new repository. This should be called course. And this course is called this design patterns. Repo to store projects for the course. Gorge in there. Chuck in a Unity get ignore. No license. Let's go. Publish. And now let's make a new project. If we go, where's my installs? Cancel installs, official releases, install editor. Oh, we do have an LTS. Yes, I don't need Android build support or Mac. I will include WebGL. Yeah, why not? And the doc. Beautiful. And that might be a good time to end it actually, because I really need to go to the loo, and that's going to take a while to download, and then I'm going to uninstall some stuff. So yeah, I will see you guys later this afternoon. I'm going to do some jobs. Hell yeah, I'm loving this course though. I